Hello, I'm Joseph. I'm a recent graduate from Carnegie Mellon University, now working at Google. I'm here to present our paper, A Theory of Tagged Objects. So the focus of this talk and of this paper is really a formal type theory that describes hierarchical object-oriented tags. And I guess more specifically, when we started out writing this paper, we really focused on the idea of instance checking, which is more commonly seen in the instance of construct in Java. And when we talk about tags and instance checking, we really want to talk about what goes into the object, into the class when we try to compare an object or check an object for it. So we can consider a class of having an interface or its type, some implementation in code, and also this tag, which is what we use to really check whether or not an object is of a certain class. To visualize this better, we can go into a more formal representation of Java, Featherweight Java, done by Pierce. And here, in Featherweight Java, Pierce and his colleagues provide subtyping and computational rules for Java. And in that, there is one that I wanted to point out, the subtyping rule, which for C being subtyped by D, which are C and D being classes, is really based not on the interface or implementation of C, but rather the fact that it is defined that C extends D. That this is that the subtyping relation is based on the fact that C and D are tags. But the problem, and since, well, this is a good start, we now really have some intuition about what tags are. The problem with Featherweight Java is that it's not a very foundational model. I said before that we wanted a formal foundational model for instance checking and hierarchical tags. But Featherweight Java combines different aspects of classes, like the implementation, with tags and puts them into one construct, which is not very useful. We'd like to have tags separate. And there are also other languages that are not like Java and have first-class classes, like the languages shown before, like type bracket and so forth. And in these, a model for first-class classes would take advantage of the fact that tags have the possibility of being generated at runtime. And so these types of dynamic tags can be seen in not an object-oriented language, but rather a functional one, standard ML, where Harper and Stone provides also a formal semantics for this, where they call the exception type of standard ML an extensible open sum, which you can add tags to. For example, like shown before here, where you can define new exceptions. And then you can go and pattern match against these exceptions using the handle construct. And so you can dynamically generate tags, and then you can pattern match or instance check against them using this handle construct. And while that's useful, and it does inform us that there is a way to model dynamic tags, the SMO version is obviously flat, because they really only care about having runtime exceptions and not really any sort of class hierarchy. However, there is another paper, Glew, type dispatch for name hierarchical types, which presents a model for hierarchical tags. And this hierarchy is found in the dynamic semantics of the model, where he is able to create a hierarchical store during runtime. But then in his types, none of this hierarchy is ever shown. For example, there is a type tag tau for the type that you want to match with the tag. He has a new tag that does tag tau, but he also has this subtag, which you can provide a tag in its second argument, but yet it never shows up in the type. It ends up being still a tag tau. And furthermore, there's also the make tag expression, which takes an object and tries to give it a tag, but it doesn't tell you what tag it's tagged with. This also, once again, just gives you a tagged object. So here, to summarize, we have three different formal models for object-oriented programming, but they all are missing something that really gives us a good foundation, formal foundation for hierarchical tags. Featherweight Java, this being not foundational, standard ML doesn't have any hierarchy, and Glew's model just doesn't really reflect any of the hierarchy in the types. We created a model that is able to have all these things and be able to provide static types for instance checking with first-class classes. So to motivate this language a little further, we have some examples in a simple source object-oriented language with first-class classes. So here we have the pretty simple counter object, which just has the field val and some method inc that increments the object value. And we could also have, and so want to be able to emulate this. We also want to emulate some sort of subclassing. So we'd also want to, so for example, we could have a resettable counter that adds a reset method to this. And notice that in our source language and also in our core language, we don't have any inheritance of code. This is not really part of our model, and this distracts from the topic of tags. And we can also have, and obviously, since we were talking so much about instance checking, we also need some sort of way to check an object against a class with the match construct here, which in this example, if we know that our object is a resettable class, then we can just call the reset method instead of creating a new counter with the value 0. So with this, we can start moving on into the core calculus. To construct it, we start with the simply typed Lambda calculus. You have your standard variable function application Lambda function type. And since we want to start encoding objects into this language, we first add records. So now we can start emulating fields and methods. But we'd also know that objects could be self-referential. So we're going to add some recursive types, in this case, iso-recursive types, and a let-rec expression, so a recursive let for notational convenience. And with this, we can emulate our counter object in our language now, and we can encode it using a recursive constructor that creates an iso-recursive record. And for accessing its values, then we just have to basically unfold the recursive record and just access its fields. So now, since we are talking about a theory of tags, we're going to need a way to introduce tags, where tau in this case is the interface that we want to pair the tag with. And obviously, this is a theory of hierarchical tags. So we're going to need subtags. And we're going to be able to now extend previous tags with subtags. But one thing to note is now that we added subtags, we have to add more things to our language, including subtyping, because in correctly typing our subtagging rule, we're going to need to be able to make sure that the interfaces of the parent tag and the subtag actually make sense in a subtyping relationship. And so since we have subtyping, we can just throw in the top type there. But there's also one last thing that I kind of glided over in the presentation of subtags, is that the fact that now we have this x in our types. And obviously x is not a type in and of itself. And so we're definitely going to need some sort of dependent types. In this case, we can consider tau tag a name-dependent type. But even so, in order to really have type safety, we're going to need to change our function type to a dependent function. And with that, we can now create tags dynamically. You can see in the make RC, or make resettable counter definition, we have a lambda that's able to take in a tag, a counter, or basically a tag that represents a counter, and it provides a subtag for resettable counters. And as you can see, the type there would require a dependent type in order for the tag to really make sense. Since we now have tags, we want to be able to apply them to objects. And so we have this new expression that takes an expression and then wraps a tag with it. And now we have this new type tag x to represent the newly tagged object. You can note that it's different from Glew's by the fact that we have this new x, meaning that our tagged objects also need name-dependent types. So now we can go back to our simple untagged counter object. We can just give it some tags. It's fairly simple. We just define a tag that has the right interface, and then we just wrap it with the new expression with the implementation that we had before. And so with this, we go straight to the meat of our calculus, the pattern matching, or the instance checking. And it looks very similar to prior pattern matching expressions. And at first glance, our first attempt at giving a type for this expression was very similar to how it's presented in most common literature, with maybe one small exception of this clause here that just says that we can make sure that tags are in the same hierarchy tree. This makes it nice that we can't compare tags of different hierarchies. And otherwise, it's fairly similar to the previous definitions of match, where you would, in the success clause, you would basically strip the tag and then bind the underlying value to a variable and use it in the success clause. But there is a slight problem with this definition of the type. So suppose we have some sort of hierarchy where A is a tag, which is subtagged by B, subtagged, and B is subtagged by C. And then we create an O that is of tagged A, and we create it with C. And then we go and pattern match this against B. So now we know that that O prime has the underlying type of B. But what if we wanted to see if O prime could match against C? Well, in our previous typing rules, this isn't possible because we had stripped the tag from our success clause. And so we can't take O prime and try to see if it can work with the interface paired with C. Instead, we really should be treating O prime as being tagged with B, which gives us this new typing rule, the final typing rule, where what we really do is take the success clause and have the object or the expression be as if it was tagged with the tag that we were pattern matching against instead of stripping the tag. And so with this, it means that we actually need a special expression just for extracting the tag out of extracting the expression out of tagged expressions and just dropping the tag. And this is a somewhat surprising development, and it probably means that if we wanted to add some sort of object-oriented stuff to functional languages, we'd probably need something similar with the idea that the match can't really strip tags, but instead we need a dedicated extract expression to do that for us. And so with this, we can now fulfill another part of our what we want set, which is the fact that we can now have a function that takes in a counter and just reset it. Here we just need to match against the tag and then extract out the expression, extract out the record, and then recursive record, and then call the reset function in it. And finally, we are now able to also encode the counter class. Previously in our examples, we actually just had let expressions just bind the tag to one variable and then bind the implementation to another variable. But for the class, what we really want to do is have the tag and the constructor function for this class be paired together. But obviously, this means that the second clause is dependent on the first. So yes, we're going to need dependent sums. And for the most part, this is this counterexample explains morally how we do a translation from the source language to this core calculus. Although in our paper we have a more formal type-directed translation that is slightly more complicated due to the fact that classes themselves can be self-referential and will need more recursive types. And so this is the final calculus that we have, going through all these different cases. And you would also notice that we have a new syntactic class just for names. This is due to the fact that due to some details in the dynamic semantics, we're going to need a separate class for names in order to facilitate the type safety theorems, namely progress and preservation. And we also have an implementation in Wyvern for this idea of hierarchical tags. It roughly follows the same semantics given in the core calculus that I just presented. We have also some extra optional features, like this comprises keyword that is able to seal a tag with a set of subtags, and therefore limit the amount of subtags we can give to a tag. And this allows us to simulate data types like in functional programming languages. And so we have a hierarchical tag, a formal foundation for hierarchical tag checking with first-class classes. This is pretty much an extension of Glew's calculus with types that can track the hierarchy of tags. And you can also see this as a way to add nominal types in a structurally typed foundation, and it's similar so add nominal types to a structurally typed foundation. So it is more of a formal foundation view of nominal types, and later Tim will add brand objects in a more language implementation view of this topic. So thank you for listening.
Plenty of time for questions. We'll ask you to use the microphones if possible, because things are being taped.
Do I understand correctly that these are referentially transparent? So if you have two subtags, they're basically considered the same?
As in, no, they are not considered the same.
Oh, so when you're doing your type system, it can tell the difference between two different subtags.
Let's see, we can go back to one of the slides. Well, you see in the, let's see. Yep. Yep. Oops.
A subtag creates an instance of C,
Yeah.
a new instance of C.
So
Understood. Thanks.
but no, it's not referentially transparent. We had an example earlier where we had a function that returns subtags, but those subtags each aren't the same. But in that case, we had a dependent type that shows that they aren't the same.
Right, so you referred to Featherweight Java.
Uh-huh.
You referred to it as Pierce et al. It's actually Igarashi et al.
Oh, okay.
Bentley is the et, I'm the al.
Sorry.
And you said it was not foundational. So them's fighting words. In what sense do you think it is not foundational and your work is foundational?
I think the problem is that for our case, we wanted to be able to separate the idea of classes from the idea of tags. And So, from what I understand of Featherweight Java, there's no real separation between classes and tags in general.
I couldn't tell you because I didn't understand your definition of tag. But let's take that as a given.
Okay.
But why on earth is that the criterion for being foundational?
I mean, if you just wanted to break up the idea of class into more specific or more fundamental parts. So if we have implementation, interface, or
Sorry, I didn't mean to interrupt, but I just wanted to add, foundational may have been the wrong word. Maybe the right word would have been based on type theory in such a way that you can, in the tradition of object encoding, such as the Bruce et al. Comparing object encodings paper, where you look at classes and objects as in the way that they can be implemented in terms of the standard type theory, the Lambda calculus. There's a missing bit in previous theories, and that missing bit is what do you do with tags and instance of checks? And so we're trying to fill in that missing bit. So yes, I agree, FJ is a great foundation for Java, but it's not a foundation that is in terms of kind of Lambda calculus-based type theory.
Okay, so if you're taking your criterion as based on complicated encodings of objects in other calculi that we know about, then the answer is yes, it's not foundational. We were trying to avoid those complicated encodings. I completely agree with you. There's a different sense in which one might ask for something to be foundational, which is that it satisfies a propositions as types interpretation. And the Lambda calculus on which you're building and the notions of records on which you're building all satisfy that kind of interpretation, which is indeed a wonderful property.
okay.
And I will cheerfully admit that Featherweight Java does not have any kind of propositions as types interpretation. Do tags.
Well, it's an interesting question.
It's okay to say you don't know.
Yeah, I don't really know.
So that's a thing to look at, and,
Yeah.
and you know, if it does, I think that is a very interesting property, and that would be a wonderful thing to bring out.
Okay.
I suspect that it doesn't,
Okay.
but
All right, so something I didn't understand was sort of exactly the role that subtyping plays in this theory. I didn't understand the role that subtyping plays in this theory, just because based on these other complicated encodings, they usually had to be existentials and bounds and all that good stuff that Kim knows so much about to get subtyping to work the way you'd expect it down at the encoding level. And so I didn't see any of that complication here. So I guess I'm not sure what the subtyping story is.
I think for the most part, we stuck with the, I guess, the basic story of subtyping in a structurally typed foundation.
I don't know what you mean by the basic story. So you could be talking about like an Abadi-Carnelli calculus that doesn't do the encoding, but it seems like you're talking about encodings, and so the only ones I know about that do the encodings use existentials and bounds, to get that subtyping.
Structural as opposed to null.
Right. So if you only, is this only, I guess this is only, I guess I didn't see a definition of subtyping, so.
Yeah, I mean, our paper does actually have a definition of.
And is it
subtyping.
based on the tags only? And there's
No, we added the subtyping rules for the other parts of the calculus.
Okay, I'll have to go read it.
I'm going to take another guess at what this talks about. Years ago, I used to work in type theory. We developed, actually, I think the first theory of subtyping, but we never made that claim at the time, which was for structural typing in Emerald. And a lot of people were then working on nominal type systems, and they said, what you did is not related to what we're working on. The real languages use nominal types, and everything you did is irrelevant. And my reaction was, Well, no, because you want structural typing as well, because if you don't have structural typing, you don't have soundness. You're going to be invoking methods that aren't there. Essentially, the nominal type systems say it's structurally sound, and we explicitly said it was. There's an explicit relationship. This inherits from that, or this is a subtype of that declared. Right? And I think what this work is doing is separating out these two pieces, finally, and saying that Featherweight Java's type system is a sound structural type system plus tags, where the plus tags part encodes this business of it was declared that way. In addition to having the right methods, we declared them to have the right methods. Is that about right?
Sounds about right.
Okay, thanks very much.
Thank you.